and I'm sharing my screen. Somebody just confirm whether you can see it or not.
Yes, sir.
Okay, great.
Yes, sir.
And you can see my full screen, right?
Yes, sir.
Yes.
Okay. So let's start. Yeah. So again, for those of you who are not there that day, this is GS 683 theory, which I'm teaching this semester. If you are in GE, you will also have to do a compulsory lab next semester, which is GS 687. And so far, I have MTech 26 GE, 15 PG, and there are 2 PhDs that have registered as of today. Okay, so you have 43 students in the class, and I see 39 of them. So, okay, there are 4 people who are absent. The 2 people have not even accepted invitations for the classroom, so I'm not sure what's going on with them. So, essentially, there are 2 people who are absent today. Okay, so no problem. There'll be recording of this, and you can take a look. Okay, so TAs have actually just been announced, and some of you are my TAs. Okay, so you get in touch with me later, and in the next class I will fill up this, gap here. Okay, and the grading will be 20% quiz, mid-sem 30%. We have a little bit of flexibility with the quiz part, and some will be, according to institute norms. Okay, in-camera exam if you are not here physically. Okay, and I might just consider doing an open book with negative marking. I haven't decided yet. Most of my exams will be open quiz, except the open book, except the NSEM, which is a closed book exam. Okay, and then I'll decide. I'll tell you the individual quizzes of NSEM. How we do. Okay, so we just did that. So we'll let you know later. And at least I didn't see anybody choosing one. Okay, so more or less this is your syllabus. So there are 3 broad parts. Okay, so I'll talk about faults and shear zones to begin with, which is relevant to mineral exploration. Then we'll talk about fold thrust belt geology and balance cross sections, which is relevant to petroleum exploration. And most of this actually was developed in the petroleum industry. So that's if you're looking at, or if you're searching for petroleum in deformed terrains, and then this is something which you need to know. And this is advanced structural geology. I'll put this in the end because if you are running short of time, then maybe I will even skip stress and just do strain part. Okay. Okay, so this is where we stopped, and I took your introductions. Now let's start the course content. Okay, so to begin with, let me just get us all on the same page. Okay, in terms of what is structural geology versus what is structural engineering. Okay, so if you look at structural engineering, what happens is you take a body, you apply stress, so you know its initial configuration. Okay, you know what's going on, how much stress you're putting. You know the boundary conditions under which the deformation is taking place, and then as it deforms, you can observe that, and you can also observe the final result. Okay, so this is typically what mechanical engineers who are structural engineers are able to do. So, for example, if you are looking at a bridge, then if you load the bridge, then you can see how it will deform while you're making the bridge, and then you can have safety factors built in there so that when the deformation occurs, the bridge can withstand. In case the bridge fails, you can see what's happening before it fails. Okay, so you have a continuous path of deformation in structural engineering. Okay, since here we are dealing with mostly man-made stuff, so we can always control the initial part, the boundary conditions, the initial conditions, and observe the intermediate path and the final result. Okay, in structural geology, we work the opposite way. Okay, what you see is effectively the deformed object. Okay, and from this you are trying to infer, okay, what was the original shape, and then what happened to it so that it ended up like this. Okay, so this is you don't have any intermediate paths typically. You don't have what was the initial configuration. You don't have any idea of the stresses, the boundary conditions, even the material. Okay, all you know is the final material, the final deformed shape. Okay, the final configuration of whatever was deformed. Okay, so so that's a basic difference, and obviously doing this is much more difficult because number one, you essentially don't have all the information that you need. Number two, you can go from this to this through different paths. Okay, you don't have a single path to attain this. This is not a unique path. Okay, it's like if you're living in a hostel and you come to a classroom, different people can come to the classroom from the hostel by different paths. Okay, they've all ended up in the classroom. Okay, but they, from that you have to figure out which hostel they came from and which path they took. Okay, which is a much more difficult task than if you know which hostel you are staying in, and then basically see what happens. Okay, so the concept of balance cross section starts with this. Okay? It's the concept of retro deformation. So if you take an entire thrust belt, for example, the Himalaya, which has the main frontal thrust, there are several structures in that. The base of the Himalaya is a thrust called main Himalayan thrust, and the whole Himalayan boundary is actually wedge-shaped. We'll get into that a little bit later. But this is what you see today. Okay, and from this, you have to figure out what was its initial shape. Okay, so when I talk about balance cross section, I'll actually tell you what is the process of doing this. Okay, but for now, you just know that we see the deformed shape, and from this we have to get back to the undeformed shape. Okay, so that we can figure out where things were before they got deformed. And so if there are some rocks in there, which were in a very favorable position to be reservoir rocks, okay, we can track that, and then we can track that how it has got, deformed as deformation progressed. And so if you had to target that reservoir rock, where would you have to look for? Okay, so the process of going from here to here is basically called retro deformation, and when you do this, you basically get a balanced cross section from a deformed section. Okay, so that's what I'm talking about, right? So hopefully that is clear. If not, let me know. Okay. The other thing we have to worry about is that there are two terms which you should very clearly understand. What is a kinematic analysis and what is a dynamic analysis? Okay, I'm sure some of you know this, but in case you don't, I'm making sure that we all actually understand this. When you do a dynamic analysis, which is also in some books called a kinetic analysis, okay, you are basically looking to find out the stresses that have caused the deformation. Okay, so a dynamic analysis looks at stresses which are the cause of deformation. So it's an analysis which looks at the cause of deformation, okay? And as opposed to a kinematic analysis, where you don't look for the cause, you just look for the motions or the deformation, okay? And what do you start with? You start with observations, which are geometries, which are deformed geometries. This is what you start with. So first order of things which you actually have to go out into the field, okay? So the first order of things, what you have to do when you go out into the field is you have to quantify the deformed geometry, okay? And how do we do that? We need a reference frame to do that. So the reference frame which we use in geology is basically the vertical and horizontal planes, okay? And we look at a planar structures. And even if it's a curvilinear structure, we break it into planar parts. And then we can find its strike and dip. And with that, you can actually quantify it in three-dimensional space. Okay, and it is possible to go from strike and dip and actually, define the definition in basically a Cartesian coordinate reference frame or any reference frame you want by using transformations. Okay, some of you might know how to do that either. Also, if you've done this kind of a thing in your master's or a BSc. Okay, now we won't go into details of that, but all we need is observations which are deformed geometries. We need them to be quantified. We need them to be digital. Okay, so we as structural geologists have been digitizing deformed geometries, much before the digital era. Okay, but this is what you are doing when you are measuring strike and dip. You are digitizing deformed geometry. Okay, so once you have this, then your job is not over. Okay, your job is now to actually figure out how this formed. Okay, so you have to infer what happened and what was its original shape, and that essentially is the kinematic analysis, where you can try to restore it to its original shape. And I just showed you an example of that, which is a balance cross section. Okay, now in addition to that, if somehow you can figure out what are the stresses that cause the deformation, then your analysis is much more complete. Okay, and you come forward with a kinetic analysis. Now this itself is very difficult to do. You can balance a same cross section in many different ways. It's not a unique solution. Okay, the thing to do is you keep retro-deforming things and keep adding data. Okay, till you reach a configuration which looks like the most probable path. Okay, so the philosophy behind doing this is your balancing cross sections is that. Okay, the philosophy behind balancing cross section is you can get from here to here in many different ways. Okay, you have to keep adding data, okay, as it becomes available. So it's not like once you do the retro deformation and that's the answer. Okay, what happens is you can make a balanced cross section by just doing geology from the surface. Then as geophysical data becomes more and more available, or more and more better in resolution, then you can constrain the various paths better till you basically arrive at a configuration which looks like it's the most constrained. Okay, so this is if you've done what modeling involves, this is a kind of a modeling. This is like a geometric modeling, a kinematic modeling, you can say, where you don't have a unique path, but you essentially are trying to get back to a most probable initial state. Okay, even if you get that, it might not be the actual answer, because if you get some more data in the future, then that interpretation might change and some other interpretation might be developed. But that's the best we have at any given point. So you want to explore for hydrocarbons today, then you have to make a balanced cross section on the available data. So that's why a lot of these oil companies, they go and do seismic surveys, because that actually gives you the shallow structure best. Okay, and that's very expensive, but they have to do that before they decide on where they want to put their exploratory well. Okay, and as you know, it is very expensive. Oil exploration is a very, very expensive activity. So you got to be as sure as possible where you want to put your first well. Okay, so this is a very clear distinction: is kinematic or kinetic and dynamic analysis. For this, you look for cause, which is stresses, okay, or forces, depending on what your problem is. And in kinematic analysis, you only look for motions or the effect. And how you start that process is through observing, digitizing geometries. Okay, so hopefully that is clear. Okay, so in kinematic analysis, you can get 4 possible types of motions. Okay, so in type 1, So this is your time 1 to time 2. Okay, so type 1 is basically translation. A body can just get rigidly translated. Nothing happens, no internal deformation. Okay, it can also get rigidly rotated. Okay, it can get distorted. Okay, so so in this case, the distortion is basically recorded as strain. Okay, the shape change part is also there. In these cases, there is no shape change. Okay, what remains a square ends up as a square. Okay, might be rotated square, translated square, but it remains like a square. Whereas here, a square becomes a rhombus. Okay, because there is distortion, and there is strain, and there is shape change, and then the final part is the volume change. You can have dilatation when the volume expands, and you can have contraction. Okay, when the volume actually decreases. Okay, in 2 dimensions, that's area. Okay, so any deformation can be actually broken down into these 4 components. Okay, and that's what we do when we actually try to balance. We try and quantify all of these different components, and then try to remove that from the deformed body. Okay, now you also know that these things, this part is deviatoric strain, okay, or a result of deviatoric stress. These things, this part, okay, and this part is basically mean stress. Okay, so or mean strain. Okay, so or volume strain or dilatation or contraction. Okay, so you know all of that. So the thing which I want to distinguish is there are 4 different parts, and distortion, rotation, translation, volume change, and all the deformation we see can be broken down into these components. You can break them down into tensors. You can break them down into geometric representations of the tensors. In 3D figure, okay, I'll answer your question when I take a break. Okay. Okay. So these are the things to worry about. Okay, so here I've shown you in 2D. Okay, so instead of volume, I should strictly write area, but volume change will also be part of dilatation if the volume increases. Okay, so essentially what you do is, when you are studying deformation, is first thing you need to define what is your structural unit. Okay, now this could be a fold, right? This could be a thrust sheet. Okay, so when you are balancing cross section, the structural unit is essentially a thrust sheet. Okay, how do you define a thrust sheet? A thrust sheet is the volume of rock which is transported on a thrust point. Okay, so it's essentially the hanging wall of the thrust point. Okay, so if that's a thrust sheet, then that's your structural unit. You want to find the total displacement vector inside that thrust sheet. Okay, and split them into translation and general deformation components. Okay, this again you can break down into rigid rotation and strain. Okay, so to distinguish, now in engineering, they actually combine these 2 and they call that as strain. Okay, or sometimes they combine all these 3 and call that strain. Okay, to distinguish our usage of strain, we sometimes refer to strain as pure strain, okay, which is independent of translation and rotation, just distortion. Okay, so sometimes you'll find in textbooks people write pure strain just to emphasize that this is independent of translation and rotation. Now, this pure strain component can also have an internal rotation component, which you probably know is called vorticity. Okay, so this is external rotation, rigid rotation, but this pure strain component can also have vorticity, and we'll get into that when we talk about strain. Okay, if you don't know about it already. Okay, so that's what we do. So we define, for example, if we take MCT, we look at its thrust sheet, and we would quantify all of these, and then basically remove that. So If you remove the slip and the structures in it, you're basically removing, translation and rotation. And then ultimately you have to quantify the strain within it and then deform it. Okay, so quantifying strain is not very easy. So there are just few studies, where people have actually quantified strain. So you go, and for that you need to find a horizon where you can measure strain. For example, if you have deformed fossils, you can measure that. There are different ways of measuring strain. We'll get into that, So essentially, you need to quantify strain, quantify rotation, quantify translation, and then basically remove it. Okay. So when you remove it, when you remove the strain, then the strain ellipses basically go from what deformed values to almost undeformed values. Okay, say 1.00, etc., 1.0, as less as possible after you remove the strain. And then the shape of how the strain ellipsoid basically ends up when you restore the bed, that actually tells you how the strain was developed. Okay? And those things, again, those are details which we'll talk about when we talk about strain. Okay, so these were concepts which I kind of think you already know. So I just revised it. Okay, so that you are all on the same page. Now let me get to your questions. Prakash says in third figure also volume is changing. So does it come under dilation? In which third figure? Okay, one sec. Okay, this one. Okay, yeah. So here, assume that the area is constant. It's not changing. Okay. Short answer to your question. Okay. If it is changing, yes, then it contains internal your distortion plus volume change. Okay, so all of these components can basically be added and then removed. Okay, so the other important question, which we need to talk about is scale. Okay, and that's an important concept because whatever your question is will address some scale. Okay, so when you are working on a problem, whether you're in geo-exploration, whether you're in structural geology, whether you are in petroleum industry, okay, you will have a question or problem which you're trying to answer, which will have two scales. Number one is spatial scale, okay, and number two is temporal scale. Okay, so today let's talk about spatial scale. So what you see and perceive depends on scale. When you study deformation, exactly same thing is applicable. So the question which we try to answer is upfront is what are the scales within which we study the deformation. Now, what do we actually mean by this is the spatial scale of earth science problems would range from plate scale, where you are looking at a spatial scale of thousands of kilometers. Okay, so here you are interested in, for example, what the Indian plate is doing, or what is the Eurasian plate is doing, right? So the dimension of those plates are in thousands of kilometers. For example, when you look at the large plates, what are the velocities in those plates? Okay, and this is typically the realm of geophysics. Okay, and then if you drop an order of magnitude, go into hundreds of scales, then the problems which you are actually looking at are basically at the plate boundaries. Okay, you're not worried about what's happening inside the plates. Okay, you're more worried about what's happening at the plate boundaries. Okay, for example, then you can drop another order of magnitude to tens of kilometers, and then you get to our outcrop scale, where basically field geology kicks in, and that's essentially what you see when you go out into the field and when you map. Okay, you're typically mapping areas which are tens of kilometers in spatial extent. Okay, and then you can drop another, order of magnitude, get into 1 kilometer or less, and then you are essentially looking at things like what's happening inside a fault zone, and then you can also go into microscopic or nanoscale things, use a CM, TEM, in the lab, and get information which is relevant to this stage. Okay. Now, what you need to understand in a very clear manner is that each of the scale is actually a part of the overall picture, which is the elephant. Okay, we've all heard about blind men and the elephant story. So that is relevant. So if you are looking at things only at the scale, then you are probably looking at the tail and what's inside the tail in great detail. Okay, so you have no idea. Okay, you only know how the tail looks. You have no idea of whether the tail belongs to a camel or a, horse or an elephant. Okay. Similarly, if you're looking at only an outcrop scale, then you probably are looking at, say, just the leg of the elephant. Okay, so you get the point. So what we need to do is we first need to study at one particular scale and then try and figure out how it relates to the scale which is slightly larger than this. Okay, so if you're looking at a fall zone, right, so you can do microscopic and nano studies, you can look at microstructures, but then you have to say how it relates to the larger fault zone. Okay, and how does that fault relate to outcrop scale structures? Okay, if you're looking at outcrop scale, then you have to worry about, okay, how does it relate to this as well as this? Okay, so this typically is the realm of geology. This is the realm of geophysics, and they kind of meet at this plate boundary scale of hundreds of kilometer scale. Okay, so they come down from geophysics, and here they scale up from geology. And this is where the plate boundary problems lie. And so when we are looking at balanced cross sections, that scale is here. That's hundreds of kilometers of the Himalayan wedge is hundreds of kilometers in. If you go from the Gangetic Plain all the way to Tibet, that's in order of hundreds of kilometers. Okay. Now in this, time remains constant. Time is not varying. Okay. So given a constant time, your problems can be of any of these different scales. Okay. Right. So if I'm looking at, now let me just expand on this a little bit. So if I'm looking at thousands of kilometers, what am I interested in? What are the questions which I have to answer? And what drives all of this? Okay, so that is 10 to the power of 6 meters, okay, which is thousands of kilometers. So at this scale, okay, I'm interested in figuring out, what happens inside the plate. All my plate boundaries have collapsed to curves or straight lines. Okay, so if I'm looking at South American plate versus African plate, the boundary between them is a nice squiggly line. I really don't know what's happening here, and I'm not concerned. I'm just, interested in knowing, what is going on within this plate. And so, what are the things I can figure out? And remember, at this scale, you have to also worry about, spherical Earth. Okay, you can't worry about flat Earth. Okay, so what we do is, for example, we figure out what are the velocities in this particular plate. Okay, so we make measurements all over the place, and then we find an average velocity. Okay, and so if you're looking at a spherical Earth, then we have to find an angular velocity plus a pole along which it rotates. Okay, so what does that give us? That gives us an idea of how the plates are moving. For example, if you look at the Indian plate and the African plate boundary, okay, you see there's a divergent boundary. There's a divergent boundary not because the velocities are going in two different directions. It's because Indian plate is moving faster than the African plate in the same direction. Okay, so that's one of the things which you realize here. For example, if you look at this boundary here, it's divergent because you can see the velocities are directed in two different directions. But this is not divergent because the velocities are directed in two different directions. Okay, it is divergent because one is moving faster than the other in the same direction. Okay. Similarly here, this is a very classical mid-oceanic ridge example, and you can see that it is not, horizontal velocities, which are like east-west velocities. These are mostly northeast and northwest velocities. So this divergence is caused due to this. Okay. Also, you can observe that the plates, which are essentially your oceanic, composed of oceanic lithosphere, okay, they have much larger velocities than plates which only have continental lithosphere. Okay, so these are the insights which you have to get and figure out from looking at plate scale deformation. So here, for example, if you look at the boundary between the Indian plate and the Eurasian plate is actually moving towards east, and and the Indian plate is moving towards northeast. Okay, so the collision here is not like direct collision; it's an oblique collision. Okay, and that you must have heard, repeatedly in your studies earlier. Okay, so here, to summarize this, we are interested in figuring out what is the velocity of a plate, which direction, and how is it moving relative to its neighboring plates. Okay, and that basically allows us to figure out what the boundaries, what is the deformation regime of the boundary, whether it's extensional, whether it's compressional, or whether it is strike slip. Okay, like here, or even in New Zealand. Okay, so now at plate scale, if you have been following the literature on Himalayan arc, okay, it was kind of conceived that the Himalayan arc is a perfect arc. Okay, so if you look at thousands of kilometer scale, this you can actually fit an arc to it. That's the center here. That's the radius. You can draw an arc which will fit it perfectly from approximately here to approximately. Okay, so as you go towards the syntaxial bends, it deviates from the arc. Okay, and this has been, so the perfect Himalayan arc has been used to make, basically your hypotheses on, earthquake hazard and things like that. Okay, that's a separate topic. I won't get into it. How are GPS velocities calculated? Ankit Raj. I can take that right now. What you do is you basically take a GPS receiver, and you need, since the velocities are an order of millimeters, so you need very high precision GPS receivers, not the ones which you can hold in the hand or like your smartphones. And you have to go and make a, you get a, say, in situ rock. That's the best kind of a surface. You drill a hole in that, and you set up an antenna there and connect it to your high precision receiver. Okay, and measure its position to a millimeter level accuracy. Okay, now if it's a permanent station, then from that point onwards, you are basically collecting data, its position through time. Okay, and then you can arrive at a velocity which is essentially, what is the change in position, okay, in a year, for example, or you can average it. You can measure for 10 years and average it to a year, which will be more accurate. Okay, that's how they are calculated. Okay, does that answer your question, Ankit?
Yes, sir.
Okay, so here we have a perfect arc which has a radius of about 1696 plus minus 55 kilometers. Okay, when you look at it at thousands of kilometers scale. Now, if you drop down an order of magnitude, okay, then you get into what is called wedge scale, especially if you're looking at Himalayan example, okay, or if you're looking elsewhere, then now you can see that the boundary is not a straight line or a smooth curve. Okay, it is actually a broken line where transform faults have displaced, okay, the boundary. So here, when we start looking at the boundaries, then we see more details than we would have seen before, if we are just looking at 10 to the power of 6. Okay, so here we start focusing on the boundary. We start seeing, okay, which way the transform fault is working. how, what are these different fractures, how they've been displaced, okay, what does this indicate, okay, if you have a extensional setting, okay, and if you have a compressional setting, then the perfect arc also breaks down, and you actually have now a sinuous kind of an arc, okay, wherein you have parts of the arc which stick out. Okay, these are called salients, and they are part of the arc. So these are parts which stick out. These are convex towards the foreland, and the ones which are convex towards the foreland, or they are convex towards the hinterland. Hopefully you know this terminology. Hinterland is the interior part of the mountain belt from where everything comes. Okay, and the foreland is the frontal part of the mountain belt, which is your gangetic plate. Okay, so if it is convex, then it is called salience. If it is concave, it's called a recess. Okay, so you can clearly see that there is sinuosity. Okay, so now if you are a geophysicist and you want to say run an experiment, for example, you want to measure, you do a seismic survey, or any kind of a survey, or even a GPS survey, then you have to look at the scale very carefully. Okay, because as a geophysicist, I can come and put a station here and take it as basically, okay, this is a station which I see in the Indian plate. Okay, because my problem is thousands of kilometers. But then, if I'm looking at 10 to the power of 5, then I can say, like, okay, it is not exactly on the Indian plate, but it's in the boundary, between Eurasian and the Indian plate. Okay, so therein lies the issue. So you can interpret it in terms of it is at the frontal boundary, okay, of the Indian plate versus Indian plate. Okay, right. So if I take so now the other thing is that if you see this arc and it has its sinuosities, then the transport always occurs, in a direction which is perpendicular to the arc. Okay, so here things are getting transported from, northeast to southwest. When you come here, the transport direction is from north to south. If you go here, then your transport direction of the thrust sheets, or the material, is from northwest to southeast. Okay, so it's the transport direction of material is basically perpendicular to this arc. Okay, and if there is sinuosity, then there is more transport, obviously, where you see the salience, and less where you see the recesses. Okay, so if I'm looking here, then I want to make sections which are perpendicular to this. So when you're making balanced cross sections, when you go to this part of the Himalaya, you want to make north-south sections. When you go here, you want to make northwest-southeast sections. When you are here, you want to make northeast-southwest sections. If you go and make a north-south section here, then that will be an oblique section. Okay, so it's like true dip and apparent dip. Okay, so if you go directly perpendicular to the strike, then you are getting the true dip. If you go at an angle to the strike, then you're basically getting a apparent dip. So same thing applies when you're planning your cross section, okay, or your surveys. So you have to be careful about which is the direction you want to study. Okay. So if you look at the Himalayan wedge, then it has something called what is called a décollement. Okay, there's a basal décollement, which is called a main Himalayan thrust. And even if you don't know what it means, I will get into this when I talk about fold and thrust belts, so don't worry. So this is a main Himalayan thrust, which is at the base of the Himalayan wedge-shaped boundary. And the frontal part, so the MHT actually comes out close to the surface as the main frontal thrust. And then you have all of these thrusts, which basically asymptotically, they meet the MHT. Okay, and that is called fault soles into the décollement. Okay, we'll get again into those details when we get into the fold and thrust belt part. Okay, so the boundary doesn't look like a straight line now. It looks like this. It's a wedge-shaped boundary. Okay, that's your STD, higher Himalaya, MCT. You go further this side, you'll get the suture. Okay, so if you take a slice like this, and the direction of this slice should be perpendicular to the arc. Okay, then you will see these structures, and below that you basically have the Indian plate. Okay, so this is no man's land. This material belongs neither to the Eurasia nor Indian plate. Okay, below this is Indian plate material, and then once you go to cross the suture, then that is definitely Eurasian plate. So foreland definitely Indian plate. After suture definitely Eurasian plate. Under the décollement definitely Indian plate. This part is a mix of everything. Okay, material from the Indian plate and the Eurasian plate. Okay, so that's how the boundary looks like. So now it doesn't look like a straight line or a curve. It looks like this. Okay, so now this example was actually from Nepal. You can see Kathmandu Klipe. But if you go further east, this is your Darjeeling Sikkim Himalaya. There you actually see the wedge-shaped boundary looks something like this. Okay. Now this is very interesting because in this part, a project was done in 90s called Project In Depth by geophysicists. This was like a huge, group of scientists who came from the US and Chinese scientists, and they ran a deep seismic survey, in the Tibet plateau, and they got south into the Himalaya, and they were able to. They were the first people who this is from that study, Nelson et al. 1996, who actually were able to image this main Himalayan thrust and this huge dome, called Pangmar Dome, and also they were able to image this partially molten layer under the Tibet plateau. Okay, so there are three things that came out of that study, and you can, if you're interested, you can go and look at this paper in 1996, where they found partial molten layer under Tibet. They found this huge anticline, which is, the amplitude of which is in the order of hundreds of kilometers, and they also found this basin décollement, which is main Himalayan thrust. Now, till then, there was, controversy whether the Himalayan boundary was like the Rocky Mountains or like the Cordilleras. Okay, and again, I'll address that later when I get into full and thrust geology. But basically, the controversy was whether it has a décollement like this or it doesn't. Okay, and there were lots of arguments, lots of geologists who argued that there was no décollement, and based on, again, balanced cross sections, people said that no, there is a décollement. Okay, so there was a lot of controversy in the 90s, and it was in 1996 that they imaged this décollement, and then after that, this controversy died. Okay, now, so you have to realize that all the concepts that exist today, okay, came from geophysics because of geophysical data. That's what you can. That's what you have to use when you look at what's in the subsurface. Okay, so subsurface, you have no other way but to actually rely on geophysics. And surface, you have to rely on geology. Okay, so what you want to do is you want to have, a balanced cross section that definitely uses the surface data because that's the easiest to get to. And in addition, okay, they use geophysical data, which is more difficult to collect and interpret, okay, because then, you typically also need to worry about resolution. Okay, sometimes what you can see in geology, you cannot resolve in geophysics, okay, because the resolution you get is too coarse. Okay, so that's basically how the boundary looks and a little bit of history that went along with it. Okay, so then, right, so you've got the plate, you've got the boundary. Now if you get inside the boundary, right, which is scale of 10 to the power of 4, right, then, so here, okay, so the model here was plate motions and stresses. So this was what you were targeting. That's essentially what you wanted to understand. Here, you wanted to understand, there's a model called critical wedge model which I will not get into it today. But again, when we do fold and thrust curls at this time, I'll explain this because this is an important thing. And gradually, Himalaya is now tilting towards this model very strongly. Okay, and the next thing that comes is when you start looking at your structural unit, which is your thrust sheet. So here your structural unit is what? You remember the structural unit I talked about? It's the plate. What is the structural unit here? It is the wedge. What is the structural unit here? It is the individual thrust sheet, okay, within the wedge. Okay. What controls the geometries that develop in this deformed geometries is slip and propagation rates of faults. So once a fault grows, okay, what happens to a fault? It will do two things. Okay, number one is it will basically grow, so it will have a propagation velocity. Second thing what will happen is its hanging wall will start slipping. Okay, so what's the difference between a joint or a fracture and a fault? Is the relative motion of both sides. Okay, so as long as your slip is 0, you basically got a fracture, which has a propagation rate. Once you move a fracture into fault, which also has slip, okay, then what happens? Okay, velocity of slip plus velocity of propagation comes into play. Now, depending on which is faster, okay, which is higher, you get a slew of structures. And again, we'll talk about this in detail when we get into this scale, okay, in fold and thrust scales. And then, so in this scale, so these are the two end members. Okay, so here what happens is the slip is faster than the propagation. So at the fault tip, you actually have a fold that is developed because the slip is faster than the propagation rate of the fault. So it goes and accumulates at the tip of the fault, okay, resulting in this fold. Whereas here the slip rate is slower than the fault. So the fault basically has broken through, and wherever the fault actually bends, you have its hanging wall following the steps in the fault and bending. Okay. So loosely, this is a fault bend fold, and this is a fault propagation fold. And we'll get into this in detail, like I said earlier. Okay. So how do you, at this scale, what happens? You go out, look at mountain belts like this, you see structures like this, you digitally quantify that, and so that's the fault bend fold. Okay, example of that. That's a field example of that, and how you make a model of it. That's a fault propagation fold. Okay, so these are basically looked at in terms of these end members. Okay, and what do? You again digitize. So you have topography. Digital topography is also available now. You basically have strike and dip. And you make a map, and from a map you can make a cross section. You know all of this. Okay, so how you make a cross section? First, you transfer the topography. Okay, and then you transfer the geology. Okay, but the question here is, how deep can you go? Okay, so typically what we do is when you do an exercise like this, we can arbitrarily just cut off, make a section like this, and we can just cut it off. Yeah. Somebody else can actually complete this hinge and complete this here, and you can go even deeper. Okay, but this is based on what you see in the surface. Right? To actually be able to constrain this really well, you need geophysics data. Okay. Okay. So in this course, what I'll try to do is I'll try to talk about these three. Okay, these two I will cover in detail. And so now here what happens is if you actually drop another order of magnitude, you get into a kilometer and less, then you are in the realm of individual faults. Okay, so I'm not worrying about plate, which is here. I'm not worrying about the plate boundary, which is a wedge shape. I'm not worrying about the structural unit, which is a thrust sheet. My structural unit has collapsed now to basically a single fault zone. So all my questions are addressed to what is going on inside a fault zone. Okay, and then ultimately you have to relate to, okay, so how is that affecting things at this scale? Okay, but if I'm only working at this scale, then I'm not really interested in what's going on outside the fault zone, and all my concentration is inside this. Okay, so what happens here? Now, one of the things, if you typically study stress and strain well, then what this means is, here you can make the assumption that the material is more or less continuous. Okay, and why do we make this assumption? Because it simplifies the mathematics. Okay, so when we can do that, then we can follow very simple laws. Okay, we can follow what is called continuum mechanics. Okay, and we can ignore the imperfections. Okay, we can assume the matter is more or less continuous. They are not like broken into smaller pieces. So, for example, the grain boundaries are scaled out. You don't have to worry about individual grain boundaries. Just have to worry about the material as a whole. Okay, so at this scale, we can make those assumptions, those simplifying assumptions. But once you get down here, then you are in trouble. Okay, because if you look at through the microscope, you can actually see the grain sizes. Okay, you can see the microfaults, you can see the imperfections. Okay, then you cannot make those simplifying mathematical continuum mechanics assumptions. Okay, you will need to come up with a special way of looking at this, and basically two things are involved here. Number one, okay, grain size reduction occurs inside this, okay, due to deformation. And number two is you have deformation mechanisms which can be classified into frictional and plastic, okay, microscopic or microscopic deformation mechanisms. So we'll cover this in fair amount of detail in the first part of our syllabus. Okay, so this will be covered in detail. This is the second part of our syllabus. This will be covered in equal detail, and we'll try to relate this to this if there is time, and then we also talk about stress and strain. Okay, so that's how we are doing in time. Okay, we have some time, so let me finish this part. Okay, so if you look at any fault zone, now we are focusing on the fault. We are not worried about what's happening outside the fault zone. Then, when you are close to the surface, you'll find break, shear, gouge, which is essentially brittle. Okay, then you go a little bit deeper, you'll get what are cataclysmics. You get a little bit deeper, then you start getting myelonites, and you get really deeper, then you get foliated myelonites. Okay, you can calibrate that in terms of temperature. You can calibrate that in terms of depth, and also metamorphic phases. Okay, so the same fault zone, if you basically go deep enough, give you a myelonite. Okay, but on the surface, it actually shows brittle characteristics. Now, what controls what you will see on the surface is that where the surface is. If you give it, if it doesn't have, once the fault has developed, it has not had a whole lot of time to erode down, then you will see the brittle part. But if it has been uplifted and there has been sufficient time for it to erode down, then you might see cataclysmite. Okay, if you have more time, then you might see myelonites. Okay, so one thing, there are two important things that comes out of this. Number one is whether you call this a fault or a shear zone, it doesn't really matter, because this part of it is behaving like a fault, this part of it is behaving like a shear zone. So you can talk in terms of a brittle fault and a ductile fault, or you can talk in terms of a brittle shear zone and a ductile shear zone. Okay, so that's one important thing that comes out of it. The second important thing comes out of it is you can see that this is not a distinct plane, okay, which you are accustomed to seeing with slicken lines and slicken sites. It's a zone. Okay, so when you encounter such a zone in the field, you may or may not see a very regular surface. Okay, right? So if you don't see that, right, then if you just see break, shear, and gouge, or cataclysmite or myelonite, you don't have to worry about whether you are in a fault zone or not. Okay, you are in a fault zone. Okay, so fault rocks like myelonites, cataclysmite, break, shear, they attack fault zones. Okay, better than slicken lines and slicken sides, because slicken lines and slicken sides and planar structures develop only in exceptional conditions. Okay, whereas these rocks develop in more commonly. Okay, so if you're working in a place like Himalaya, which is okay, I'll get to your question, Soumya. Let me just finish this. So if you're working in a place called, in the region like Himalayas, then fall zones would be trackable only by fault rocks, most of the cases. Okay, and if you don't use this tracking the fall zone by fault rock approach, you'll miss a lot of fall zones. Okay, so that's what's happened in the literature, and now people are understanding fall zones much better. Okay, especially after the 90s. And I'll talk about that in fair amount of detail when we get to fall zones. Okay, so Shomya says, sir, can we draw a vertical profile for shear zone on the basis of how we observe lateral distribution of direct shear, characterisite, myelonite in field? Okay, so now that would depend on where your surface is. Okay, so the same fault. So if you are seeing laterally a breccia, a cataclysite, and a myelonite exposed in the field, very unlikely that it is the same fall zone. Okay, unless that fall zone has somehow been folded so that all the three rocks at different depths are exposed on the surface. Okay, so in the field you will typically see only this. Now, even if this fault actually folds back up like that, okay, you'd probably, not see the myelonite here unless, the folding is such that myelonite is exposed. Okay, so that will depend on what you actually observe in the field. Okay, this is a profile, depth profile. Now, if you see the same thing exposed here, it can, that would be very tricky to explain from the same fault zone. Okay, now what can happen on the surface is, you will see different parts of this formation of this structure. Okay, and we'll get into that in detail when I talk about it, fall zones. Okay, so for now, two things I want you to remember from this. Number one, the same fall zone as it goes to depth goes from brittle to ductile. Number two, fall zones can be much better recognized by fault rocks rather than your slicken lines and slicken sides. Okay. So, okay. The other thing I need you to remember is, okay, Shomya, in case of Himalayan field, have observed these units separately. Yeah, because there are multiple faults. That's what I just told you. That will be very difficult to actually relate it to the same fault. Okay, it has to be different faults. Okay, that's what I've told you. And I'll talk about this. So, let's move along and we'll discuss this in detail later. Okay, so two things I told you: fall zone, number one, tagged by fault rocks. Number two, brittle near the surface, ductile when you go down. Okay. Third thing, important thing, any fall zone is characterized by grain size reduction. Okay, so if you are in a brittle fall zone, then this is your original grain size. It will be broken down into multitude of sizes by fracturing. Okay, so that's the brittle process. So what is happening here? Grain size reduction by fracturing, which is a brittle process. If you go into a ductile shear zone, again, this was the original grain size. This is from under a microscope. These are quartz grains. They have all become, they've been grain size reduced to this. And you can see the intermediate process where, this is actually converting into smaller sizes. So this, starts on the edges of the larger grains, and ultimately it consumes the entire grain. Okay, so both places, grain size reduction. That is the fundamental process that goes on inside any fall zone. Okay, and we'll discuss that in greater detail when we get to your fault zone studies. Okay, fault scale, that's also very important. Okay, so you can see faults in a satellite imagery. Okay, so here again the same scale thing applies. You might not see the details of it. It looks like very linear, very nice clean fault. Okay, now when you come down to, so if you can see this small rectangle here, if I zero in on this part, then you actually see this. So here you can see still it's pretty linear. Okay, right? Similarly, this is even at outcrop scale, it's a pretty linear, nice normal fault from Kutch. This is from Tibet. Here, this is from near Chandigarh. Okay, these are Shivalik Rocks. They are sitting on quaternary, loose gravels. Okay, that's a very distinct boundary. Okay, so so these are actually exceptional where you can see a very distinct boundary. And when you can see that, you're lucky. You can define the fault surface and define the hanging wall. You can define the. But the trouble starts when you find a fault zone like this. Okay, so here's a hammer for scale. This is a small scale fault, but it's not showing a linear pattern at all. Okay, so the fault zone starts somewhere here and ends somewhere here. Okay, this is kind of its footwall. This is kind of its hanging wall. Okay, there is a lot of fracturing. So the other thing you see is there is distribution of grain size. So if you go to very, the central part of the fault, the grain size reduction is maximum. As you go away from that, the grain size reduction is decreasing. Okay, on both sides, and that might not be very symmetric, and we'll get into all these distributions later. Okay. And you might actually end up in a fault zone which looks like this. Okay, looks like this. Looks like this. Okay, this is completely grain size reduced fault. You can see there are parts where you can actually see the relic bedding, but most of it's been smashed. And when it gets completely grain size reduced, potter can gully this. Okay, and basically subject it to gully erosion. So, from a distinct break like this, if you end up in a fault zone like this, it'll be very hard for you to recognize it as a fault zone. Okay, but if you follow that approach, wherein you're looking for fault rocks, you're not looking for distinct breaks. Okay, then you'll be able to recognize these. Okay, so the next thing we need to worry about is, so we talked about in space. There is also an aspect which you have to worry about in time, and that's important because, here you have the same elephant story analogy, except that the time is variable. Okay, so you're not only observing parts of the elephant, okay, at a constant time, but even the time is varying. Okay, so in terms of temporal scale of deformation, you can go from structural geology, where in the Himalayas, for example, it's from 150,000 years to 55 million years, but it can range from 150,000 years to billions of years. And here in structural geology, you can expect ductile, brittle, all three kinds of deformation. But if you look at neotectonics, which is the realm of geology again, okay, here you go from about 1,000 years to 150,000 years, where the example of neotectonic deformation is this. Okay, this is quaternary gravels. Okay, then this is again a field in geology, but don't expect brittle ductile or ductile here, because in neotectonics you are close enough. You have not had enough time to basically exhume deeper structures. Okay, so you'll only see brittle. Okay, paleoseismology, same, all will be brittle. This goes from hundreds to thousands of years. Here you basically see old signatures of earthquakes. Okay, and then active tectonics, which is basically measured by GPS and how things are deforming. This is decadal scale, and seismology, which is centum scale or hundreds of years. So the earliest your record of geophysical record of earthquakes is about 100 years. and then you go into paleoseismology. So this is again the realm of geophysics. This is the realm of geology, and they come and meet here. Okay, so paleoseismologists are sedimentary geologists plus seismologists. Okay, so similarly here, same kind of a situation. Okay, you have to again address your question whether it falls in this scale, this scale, this scale, this scale. Whether how does this relate to this and this? How does this relate to this and this and this? Okay, so it's the same deformation. It's basically, you know, happened over a long period of time and has got manifested in, you know, different ways. Okay, so you have to be able to recognize that, and again, the aim should be to understand the entire elephant, okay, and how it has changed over time, okay, and what signal you have belongs to which time scale. So if you can integrate in space and time, then, you know, your product will be much better understood. Okay. So perfect time 3:23. If you have any quick questions, I can take them. Otherwise, we break for today.
Hello, sir, I'm audible.
Hello? Yes, yes, you're audible. Abhishek, you're audible.
Sir, any difference between fault and shear zone?
Fault and shear zone.
Yeah, yes, sir. Yes, sir.
What did you? Okay, so fault and shear zone, the difference is actually, like I told you, there is no real difference. Okay, but if you go in classical literature, fault zones means, you know, when the fault is behaving in a brittle manner, and shear zones means where it's basically behaving in a ductile manner. Okay, but in terms of processes, both the products are produced by simple shear. Okay, so you can look at it in terms of a fault zone is a brittle shear zone, okay, or a ductile or a shear zone is a ductile fault zone. Okay, right? So, but if you want to be classical, then for brittle, use faults, and ductile, you use shear. Okay.
Sir, shear zone can, hello, sir, one
Yes.
more thing. Shear zone can be from intercratonic and intercratonic block always.
Okay. Now that's actually a good question. But now in a shear zone, okay, even if it is a part of a craton right now, but when it formed, okay, it had to be a part of a some kind of a boundary. Okay. Now, you know, you remember Wilson cycle, right?
Yes,
okay.
Sir.
Yeah. So if you look at the Wilson cycle, then, you know, you start off with extension, then you go into convergence. Okay. You know, so you have faults, extensional faults, and compressional faults. Then you go finally into strike slip, and then the whole region becomes a part of a craton. Okay. Once the deformation dies, right? So ultimately, the parts in the craton where you can see, you know, so if you're looking at a craton, then if they consist of different blocks which have somehow been assembled together due to deformation, then the boundaries of them will have these major shear zones. Okay, like your Kaveri shear zone, okay, you know, Palghat shear zone. These are cratonic shear zones, which people think that, you know, when different parts of the or exotic terrains, you know, came together due to deformation, these were formed. If inside each cratonic block, if you get shear zones, then, you know, these are again parts of some old mountain, you know, which has got preserved now. Okay, so yes, you can see shear zones even in cratons, but then you know, they will have an earlier deformation history. Is that clear?
Okay, sir. Okay, sir.
Okay. Anything else? Okay, then if there is nothing else, you know, we'll let you know what your polls told me, and we'll work it out accordingly. Okay, so class ends here. So stop recording, stop presenting.